Hello friends, Mr. Burrell here. We're in Unit 3 talking about polynomial functions. We've talked a lot about different kinds of polynomial functions. We've talked about how to add, subtract, multiply polynomial functions. We've talked about complex numbers and operations with complex numbers. We've talked about the fundamental theorem of algebra and finding solutions. We've talked about intervals of positive and negative polynomial functions and looking at those graphs. We've talked about multiplicity. We've talked about lots of different things associated with polynomial graphs. So we're going to finish off this unit talking about some additional parts of polynomial graphs, some additional characteristics that can be handy to identify with polynomial graphs. So by the end of this lesson, by the end of this video, this is what I hope you're able to understand and accomplish. I hope you're able to determine intervals where the function is increasing or decreasing from its graph. We'll talk about increasing and decreasing. I'm wanting you to be able to identify the turning points of a function from its graph. We'll explain what those are. And identify the maximums and minimums of a function from its graph. Some of these terms might be kind of familiar. We've talked about this a little bit in Math 2. We're just going to review and extend it a little bit in this section. So some definitions of each of those things that were on that previous slide. So turning points. A turning point is an x value where the function changes direction. So, and it says that's where a local minimum or maximum occurs. So when I say where the function changes direction, that means it's going from decreasing to increasing. So the way I kind of think of turning points are as mountains or as valleys. So right here is a turning point. 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 And right here is a turning point. Anytime the graph changes direction is a turning point. We'll identify specifically what we're going to call each of those points in a bit, but for now, each of those are turning points. Any point where the function changes direction, and we usually determine that point using the x value of whatever that coordinate is. So whatever this x value is right here is how we identify that turning point. Next, we're talking about increasing intervals. So increasing intervals is where as x increases, reading from right to left, y increases. Or another way to think of that is if I was walking from left to right, anytime I'm going uphill. So I'm going to go ahead and draw on my graph. Right here, I would be going uphill, or my graph is increasing. Right here, I'd be going uphill, where my graph is increasing. And up here, I'd be going uphill, where my graph is increasing there. And we refer to those intervals using the x coordinates associated with those intervals. So for example, from this x coordinate to this x coordinate, my graph is increasing. From this x coordinate to this x coordinate, my graph is increasing. And from here to here, forever and ever and ever, my graph is increasing. Decreasing intervals, let me switch colors. Decreasing intervals are where as x increases from reading from left to right, y decreases. So as x gets bigger, y gets smaller, or where my graph is going downhill. So right here, my graph is going downhill. Right here, my graph is going downhill. And right here, my graph is going downhill. So those are the parts of my graph, or the intervals on my graph, where the function is decreasing. So, and I write those intervals in terms of the x coordinates as well. So I would be decreasing all the way from here to here, from here to here, from here to here, and from here to here, I would be decreasing. And then I would be increasing from here to here, here to here, and here on into infinity, if you can kind of see that. So those are increasing and decreasing intervals. We'll practice writing those here on the next screen. But next we're going to talk about global/absolute maximum. When I talk about a maximum, I'm talking about a mountain. We've talked about maximums before. So the global or the absolute maximum is the largest value of the function on the entire domain of the function. So if I was to look at this whole function, I'm wanting to look for the highest point of this entire function. If one exists, I'm looking for the highest point. Well, you'll notice that this point seems pretty high, but the graph keeps going up in this direction forever and ever, and up in this direction forever and ever. So like on this graph, there would not be a global maximum because there is no tallest mountain. It just keeps getting taller and taller and taller and taller. We'll see some examples on other functions where that's not the case, but the global maximum is the largest value of the entire function over the entire x-axis, the tallest mountain. The global or absolute minimum, let me switch colors again. I'm going to run out of colors. The global or absolute minimum is the smallest value of the function on the entire domain, or the lowest valley. So this is the lowest valley. And this up here was the highest mountain. So on this function, you'll notice that this point right here, I'm going to draw a big circle right here. That point right there is a global minimum because it is the lowest point on this function. It is the deepest valley of this entire function. So that's my global or absolute minimum. Now, if I want to talk about local maximums and local minimums, a local maximum is the largest value of the function within a given range. So any other maximum or any other turning point that is on a mountain is going to be considered a local maximum. So this right here is a local maximum. This right here is a local maximum because those are the tallest mountains in this short little section of the domain. That's the tallest mountains in this section of the domain. So conversely, the local minimums are the smallest values of the function within a given range. So these points right here are the lowest values within this given range, so those are local minimums. This is not a local minimum because it is the global minimum. That is the deepest valley, so besides that minimum, these are the other local valleys or the local minimum points. Okay, so those are all the different characteristics of these polynomial graphs that we're going to talk about in this lesson. So keep in mind this picture, you can kind of use it for reference. So question number 1, it says identify each of the following in the graphs below. You'll notice that this graph is very similar to the last graph from the last lesson that we discussed. So now, before we were talking about like intervals where the graph is positive or negative, now we're going to be talking about turning points, increasing and decreasing, and maximums and minimums. So first, a turning point. Where is a turning point? I'm going to label that in red. Well, a turning point is anywhere the graph changes from increasing to decreasing or decreasing to increasing, anytime it changes direction. So this is going down all the way to right here, so right there, and then it changes direction and starts to go up. So that is a turning point. We're going to identify that turning point with the x coordinate. So right here at x equals -1, that's a turning point. And that's the only one in the case of this graph. So on either side of that turning point, I'm going to have intervals of increasing or decreasing. So let me get my blue. Everywhere that the graph is going uphill or increasing, so right here, that's going to be my intervals of increasing, my increasing intervals. So you'll notice that's going from -1 all the way to, where is this going to stop increasing? It just keeps going forever and ever and ever. So my increasing intervals are from -1 to infinity. I put those in parentheses. My decreasing intervals, you'll notice on this other side where my graph is coming down as I walk from left to right, as I kind of have this little downhill slope, that's where my graph is decreasing. From -infinity, so from all the way to the left, all the way until I hit this red dotted line here at -1. Those are my decreasing intervals. So now I'm going to go ahead and look for my global maximum. Do I have any global maximum? So I'm looking for a mountain. I'm looking for the tallest mountain over this entire graph. Well, if I keep climbing up and up and up and up in either of these directions, you'll notice I will never cap off and form a mountain at all. So there isn't a global maximum. So I'll just put like a line here, or I'll say none. There is not a global or absolute maximum. There is no biggest mountain. Now, on the other hand, a global minimum A global minimum is going to be the lowest value over this whole function. You'll notice in this whole graph, I will never get lower than this point right here. I will never get lower than this point. So the x-coordinate of that point right there, where my global minimum is going to be x equals -1. You see that? X equals -1 right here. That's where my global minimum is going to be. X equals -1. That point, if you wanted to write the point, it's going to be -1, -4, because it's -1 in the x direction, -4 in the y direction. But we're mostly concerned with the x value, because those are the input values for all these different functions. The x values are. So that's my global minimum. Now for my, for my local minimums and maximums, well, there's no other turning points. There are no other turning points. So since this only turning point that I have was a global minimum, there's no other local maximums or local minimums. So I'm done. I'm done identifying all the characteristics associated with this graph of this function. So that would be my final answer. I'm done. Good. Yay! Good. Okay. Let's look at graph number 2. It says identify each of the following in the graphs below. So first, I'm going to identify a turning point. I'm going to identify all my turning points. Here I'm going to mark them in red. So this is a turning point. I'm going to go ahead and draw a little dotted line down to that turning point. Here's a turning point, and here's a turning point. This is right about here. So my turning points, again, are any point on the graph where the graph changes directions, okay? So the x values, where I have turning points on this graph, it looks like at -1.5, 2, and 4. Those are where each of my turning points are. So notice, I kind of pointed this out on the last slide, but notice that these points right here, these turning points, will also be my global or local maximum and minimums when I get here. Those points will fall into one of those categories. And my increasing and decreasing intervals will be between and around those turning points. For example, so if I want to come in here and look at all my increasing intervals, I'm looking for anywhere that the graph is going uphill, walking from left to right. So from left to right, I'm walking uphill right here, then I go back downhill, and then right here I'm walking uphill. So my increasing intervals, I'm going from this red dotted line to this red dot right here, so that's from -1.5 to +2. -1.5 to +2. Put that in parentheses. That's the interval over which this graph is increasing. Now, if I want to look at my decreasing intervals, I'm going to go ahead and color in everywhere where my graph is going downhill, walking from left to right. You'll notice that I'm going downhill from -infinity all the way down to this red line right here, which is at -1.5. And then I'm decreasing again. There's another interval where I'm decreasing, so I'm going to separate that with a comma, from 2 all the way to 4. And you'll notice I missed an interval of increasing. I forgot this very rightmost part right here, so I'm also increasing from 4 to infinity. Notice, here's -1.5. That was one of my turning points. 2 was one of my turning points right here. 4 was one of my turning points. So the endpoints of each of these increasing and decreasing intervals are going to be one of those turning points. Now, let's look for a global maximum. Is there a global maximum? Let's see here. So a global maximum, let's do in green here. Global maximum is going to be my highest mountain, the highest point on this graph. Well, this graph is going to keep going up forever and ever and ever, so there will not be a highest point on this graph. So there is no global maximum. Not applicable, none. Global minimum, on the other hand, let's look at the lowest point on this graph. That lowest point is going to be right here. So I do have a global minimum at x equals -1.5. Again, that was one of my turning points. I knew it was going to pop up somewhere down here. So if that's my global minimum, now I'm going to go ahead and look for my local maximum and my local minimums. So my maximums, I'm looking for any other mountains in this range. So here's a mountain, here's a little peak right here at x equals 2. There's no other maximums, there's no other mountains. And here's a valley. So my the other valley that I have, besides my absolute valley, my global minimum, the other local minimum I have is at x equals 4. So notice, here's negative 1.5, here's positive 2, here's 4. Each of those turning points found a place in my global and local maximums and minimums. And those are all the characteristics that I wanted to find pertaining to this graph, this function. Okay, good. So now question 3, this is the last one. We're going to find the turning points, increasing and decreasing intervals, global maximum and minimum, and local maximum and minimum. So first I'm going to identify my turning points. Anytime the graph changes direction, you'll notice in each of these are already colored in red. Those are my turning points. At x equals, it even gives me the x values in each of these. X equals negative 3, x equals negative 1, x equals 2, and x equals 4 are each of my turning points. So each of those x values as turning points are going to pop up in one of these 4 boxes down here as one of my minimums or maximums. And my increasing intervals and my decreasing intervals are going to be right nestled in here between these. So my increasing intervals, again, are anywhere my graph is going uphill. So right here, my graph is going uphill, and right here, my graph is going uphill. So I'm increasing according to my x values. Let's draw these dotted lines again. According to these x values, boom, 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 boom. According to these x values, my graph is increasing from negative infinity all the way up to negative 3. My graph is increasing from negative 1 all the way up to positive 2. And my graph is increasing from 4 all the way to infinity. So from 4 all the way to infinity. Now let's look at where my graph is decreasing or going downhill. My graph is going downhill right here and right here, it looks like. There are 2 places where my graph is going downhill. My computer wants to shut me down, but alas, we're not going to let it. Thank you. It's going down from here at negative 3 all the way to negative 1. So decreasing from negative 3 to negative 1. I'm decreasing again from 2 all the way to 4. 2 to 4. So those are the intervals where my graphs are increasing and decreasing. And notice each of these turning points kind of pop up in each of these intervals. Negative 3, negative 1, 2, 4. They pop up in those intervals. Now let's look for my global maximum and my global minimum if there is one. So my global maximum is going to be the highest point on this graph. Well, this kind of for a second looks like the highest point, but you notice over here, the graph's going to keep going up forever and ever and ever and ever. So there will never be a highest point. It just keeps going to infinity. So there's no global maximum, NA, none. Global minimum. If I'm looking for a global minimum, I'm looking for the lowest point, the lowest valley on this graph. Well, the lowest point seems like it could be here, but look here. This arrow means this graph's going to keep going forever and ever and ever. So there's not a global minimum either. And that's okay. Sometimes that's going to be the case. Now, that means all these other turning points are either going to be local minimums or local maximums. So my local maximums are going to be all my mountains. You'll notice I have a mountain here and a mountain here. So at x equals negative 3 and positive 2, I have my local maximums. And my valleys, or my low points, are here and here at negative 1 and positive 4. So x equals negative 1 and positive 4 is where my minimums are in this graph, my local minimums. So, Mr. Bro, why are we talking about this? Why are we talking about turning points, increasing intervals, decreasing intervals, etc., etc., etc.? There's lots of application in marketing, in like stocks, tracking money, tracking trends, where identifying these specific parts can be really helpful. Think of like the stock market. Stockbrokers have to watch the graphs of pertaining to the changes of the value of these different companies really closely to see, okay, when is the trend going up? When is this company making money? And at what point did it start losing money? At what point does it start making money again? There's constant up and downs, constant increasing and decreasing intervals. And the maximums and the minimums represent points of high money and low money. So that's just one example of where analyzing a graph like this would be helpful pertaining to a situation like that. So at the end of this lesson, these are the things that I hope you understand. I want you to be able to determine intervals where the function is increasing or decreasing from its graph, identify the turning points of a function from its graph, and identify the maximums and minimums of a function from its graph. So I hope that was helpful. Please let me know if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.